So sampling theorem. So sampling theorem, which is Nyquist theorem. So also we can call as a Nyquist theorem. The sampling theorem that we will see. Okay. Basically, we already know sampling frequency, sampling rate. What is sampling rate? Within the time period, means within the second, how many samples taken. It is sampling rate and sampling frequency Fs. That's 1 by T. For consider as a sampling 1 by Ts, and then Nyquist rate. That Fs is equal to twice the highest frequency. So we see in last videos. And now we just consider this a band. So for sampling frequency, uh, this is the basic band limited signal. So minus omega, that means frequency minus and plus frequency represented as W. So this is basic band limited signal. So see this. Yeah, in sampling frequency, there are three conditions present in sampling frequency. One is Fs less than 2W, that means Fs equal to 2W, and Fs higher than rate, that means it is high, that Fs is twice the highest frequency. So there are three conditions are sampling theorem. The first one is the following figure. It's the sample rate is higher rate than 2W, twice the highest frequency. We already said the sampling, that Fs should be twice the highest frequency. So if the sampling is twice the highest frequency, so it should be like that. There is no overlap and there is no information lost. So recovery is possible. We can easily get it from receiver. So the main concept is the sampling frequency that should be highest, twice the highest frequency. Sampling rate that should be twice the highest frequency. Then we get the signal like that. The equation, I just now said Fs is equal to 2W. If it is equal to 2W, the sampling frequency, it is not twice the highest frequency. If it is equal to twice the frequency, what will be happen? So example, this is sampling graph. So it started perfectly. The results shown in the figure. So information, it is not lost. So there is no information lost. So it's a correct sampling. But practically it is not possible. Theoretically it is okay, but practically it is not possible. There is no perfect start and end time of the signal. So that's why we go for the highest frequency for taking sampling. So this is a critical condition. Third one, the sampling frequency is less than twice the highest frequency. So if the sampling frequency is less than twice the highest frequency, then the pattern will be like that. Every second, every signal get it mixed up and overlapped. So because of that, the signal might be lost. So this phenomena, this overlapping condition, we can call as aliasing. You know, aliasing happened because of sampling frequency is less than twice the highest frequency. So this will be mixed up. Though, so this is a condition we can call as aliasing. So low pass sampling, aliasing and low pass sampling. So aliasing is a phenomena. So high frequency component in the spectrum in the signal. Just now we saw what is aliasing. Because of sampling theorem is less than twice the frequency, automatically it's overlapping. That is called as aliasing. This phenomena, in theoretically, we can say highest frequency component in the spectrum of signal. In PCM, pulse code modulation, the transmitter side, for reduce this effect of aliasing, that overlapping, the information getting lost. So we have to avoid that. We are using low pass anti-aliasing filter in transmitter side. There is a pulse code modulation. That pulse code modulation, that pulse code modulation in the transmitter and receiver. There is a two, every technique having transmitter and receiver. The pulse code modulation also having transmitter and receiver. In the transmitter side, before taking the sample, so we have to use low pass filter. That low pass filter name we can call as a low pass anti-aliasing filter because it allow only low pass component. It eliminate the high frequency component. That's high frequency component we can call as here as aliasing. So avoid the aliasing. So we are using low pass anti-aliasing filter that will be employed employ in transmitter side. The choice of having sampling rate than highest rate also helps the easier design of the reconstruction filter at the receiver. Okay, so sampling, we saw just now what is sampling and sampling value, the value of the function at the sampling points and sampling interval, that should be a fixed one. Optimum sampling rate depends upon the maximum frequency component percent, that is the optimum sampling. So these are the basic criteria in sampling, the aliasing, and low pass sampling, then low pass anti-aliasing filter. So these characteristics are we saw just now. So in this video we already seen sampling theorem. So in the sampling theorem there are three main criteria. So first criteria, sampling frequency is twice the highest frequency, that means higher rate. So no problem, that is good, that's a correct procedure. If it is equal, it is also no problem, but practically it is too difficult. But if it is less, then we get the problem. The signal is getting overlapped. The aliasing effect will be occur. So avoid, basically the aliasing, given the definition as it's a phenomenon of high frequency component in the spectrum of the signal. So we have to avoid that high frequency component. So low pass anti-aliasing filter, it is present before sampling in PCM, pulse code modulation transmitter. It is present. So this signal, this anti-aliasing filter will be eliminate the high frequency component and allow the low frequency component. So this will be reduce the aliasing effect. Okay. So this total uh, thing after the sampling rate higher than Nyquist rate, that should be help to easier design to reconstruction filter at the receiver. That is very important. Once the sampling rate taken, so twice the highest frequency it is get it from, twice the highest frequency if it is uh, in the sampling rate, then that is used for easier to design the reconstruction of filter at the receiver side, because if it is overlapped we can't easy to reconstruct. Okay, so if it is twice the highest frequency, then easier to reconstruct the receiver side. Okay, thank you.